Dear friends, welcome to this small YouTube channel AMP Power System Workshop. We are now discussing about this short circuit calculation. As you are aware that it is under section 7 or session 7, you can say other way. And in this session 7 we have already completed two video. First video we have demonstrated what is the relation amongst the percentage impedance per unit impedance ohmic value of any power equipment and how to calculate how to represent the impedance, what is this relation between resistance and reactance, that we have discussed in detail. In the second video under the session 7 we have calculated the short circuit current by ohmic method. Now we will calculate the same short circuit current using per unit impedance, and we will show that both the results are identical. If you recall rightly, last time we considered a typical network. We will consider the same network. It is not different. Same network with the same cable, same equipment, and finally we will calculate the short circuit current, and let's see where we can reach, whether the short circuit current calculation using by unit method or per unit method is whether it is same like ohmic method or not. So let us start the session workshop. Now as we said before, our network is same. Here our network is, there is a utility, that utility which is supplying, this is a typical plant which has this type of network, and in this network the utility, this plant, suppose this is a cement plant, or it can be maybe paper plant, or it can be a small factory, or it may be a small processing factory, a fruit juice factory, or hatcheries factory, any type of factory. Typically it is factory. There is 11 kV network is passing by the side of the factory, from where the utility company or the power generation company or the distribution company has given a connection to this plant owner at 11 kV. That utility details we do not know the utility details. There will be a power generator, transformer, all this thing, and ultimately 11 kV power supply is maybe overhead line, or it may be 11 kV is underground cable with the substation. From the substation they have given one feeder for this plant. That system is represented by 11 kV, and this utility system, the fault level is a 50 MVA at 11 kV. That is the data they have given, and from that utility the feeder has been taken, or the cable from the utility we have taken the power supply. Immediately after the utility, or the utility means it may be overhead line or for the substation, we have put one transformer as per our plant requirement. Our plant requirement is 50 kVA, 500 kVA means half MVA. So accordingly we have put a 500 kVA transformer, that is because this plant is a 415 volt low voltage plant. So this transformer is 11 kV by 415 volt, and the impedance of this transformer is percentage impedance Z equal to 4.5%. It is the same data as we used before. And then through the cable, this is one of the cable, that cable is connected to the low voltage. It is a low voltage switch gear. This switch gear is a low voltage switch gear. You can say LV switch gear 1. You can say LV switch gear 1. That is the first switch gear from where it is connected. And as this is a utility power can switch off at any time, as I said before. So there should be a emergency power supply arrangement. That emergency power supply, or it can be running in parallel with the utility. So that utility power, that generating power unit, it is installed by the owner in his plant, in his own plant. It has not come from the utility, because this generator is using as a backup power for the utility, as well as based on the requirement it can be run in parallel. So this is a generator is the same size as 500 kV, because this generator has to take care of the plant in absence of utility. So this generator has the same capacity 500 kVA, and it is at 415 volt. And the parts I already discussed about the impedance of the generator. There are three types of impedance: transient impedance, subtangent impedance, and the synchronous impedance. Subtangent impedance is the first in impedance, which is very low value. For the subtangent period, current is asymmetrical and high value, but we are considering it is a tangent reactance 10%, you can say another way. And then there is the same size of cable, and the impedance of the cable is 0.001 ohm, and then connected to the switch gear. From the switch gear there is a direct one motor is connected, 200 HP motor, 415 volt, and impedance of this motor is 25%. It is connected by a cable. That cable impedance is 0.002 ohm. And because I already said that cable impedance we got directly from the your cable data sheet, where it is given in resistance and reactance value, and from the resistance and reactance we know we can calculate the z equals to how much? Z equal to root of r square plus x square. We have used this formula. By this formula we can calculate the ohm from the cable data sheet. That's why the cables always represented by the ohm. That is, it is put over here ohm. Where is my duster? And then, so that is the cable ohmic value. Now next part is this cable is connected to a motor. That motor is a 25% impedance, 200 HP, we have already said. And the second cable is connected to the another switch gear, which is located slightly away. That is also in the low voltage switch gear, but suppose it is a switch gear 2 that is located near slightly away from this, and that is connected by this cable, and then it is going from the switch gear. There is also another same motor, same size of motor, and there is a transformer. Now our intention to calculate the fault current at this bus. How much fault current will be here? That is, we need to calculate. Suppose we can say the bus number 1. So when we are going to calculate the bus number 1, we have already calculated by ohmic value, and we got the short circuit current. We rounded to 20 kilioampere, but actually that short circuit current we calculated, if you recall, 240 volt by your impedance value. Impedance value was we consider 0.12. Actually that was rounded. It is actually, the figure was 0.012, 0.01174. That is the value, original value. We rounded to 1.2. That is the ohmic value. We rounded this figure 1 by Z, equivalent impedance. But if you put 0.0014, it will come 0.0014. It will come about 20,400 ampere. So that is the short circuit current we get from the ohmic method. When we use 0.012, it comes 20 kiloampere round figure. We rounded it, but actually this original, if you recall, that Z equal to 85.15, and if we make 1 by Z, that equal to coming 0.01174. Okay. So then we calculate I short circuit. How we calculated? 240 phase voltage divided by that per phase impedance, that is your that is equal to 0.01174. If you calculate this, it will come 20,400 ampere. That is we get last time. Okay. So we will see now how much we can get from here. So now here we have to calculate all this impedance value in the per unit value. That is the first job we have to do. Now for that, it is for the utility. We calculated a utility ohmic value before. But when you go to the per unit method, is very simple. Any utility per unit value, that equal to in the case of per unit value, what we said, we have to first consider two things. One is a base MVA, and then is a base KVA. KV, not KVA, KV. Last time a pronunciation, maybe you can feel it is KVA, but it is KV. So our base MVA here we considering 1 MVA base, and our base voltage is a 0.415 kV. That is our base voltage. Based on this is your base MVA and this is base KV. Based on that, we will calculate all the per unit impedance. Now for the utility, when you go for the utility per unit impedance, based on the 1 MVA base, that is very simple. That is equal to base MVA. Formula is MVA base MVA divided by what is divided by your rated MVA or short circuit MVA or rated MVA rated, you can say MVA rated. So here how much? MVA is a 1, our base MVA 1, and rated MVA how much? 50 kVA, 50 MVA. That will give you 0.02. That is the 0.02 per unit. That is the impedance. That impedance we have represented over here, 0.02 unit per unit impedance. This actually, you may say, you can calculate this in different way also. You can first calculate the how much ohmic value of this. That is, we know the ohmic value, we know kVA square by MVA. So if you calculate the ohmic value at 11 kV, that equal to how much? kVA square, 11 square by MVA 50 MVA. That is at 11 kV. Now we said that if you want to transfer to the 415 volt, what is the formula? Into 0.415 divided by 11 square, like a transformer. This is on 415 volt. This is the ohmic value. This ohmic value, when you convert to the per unit impedance, the formula is very simple. That equal to your, what is this? That is this ohmic value, if you calculate to 415 on the 415 volt, how much per unit impedance, that is equal to base MVA by base KVA. Base KVA how much? 0.0415. That is square. If this is a base MVA, formula is what is the ohmic value? Ohmic value of this system at the rated at that voltage 415 volt side. This is the value. This is the value for 11 kV, and then you convert to 415 volt. That is the ohmic value. Ohmic value into base MVA by base KV square is the per unit impedance at 415 volt. So if you see this thing, these are this cancelled, these are this cancelled. So what you are leaving over 1 by 50. That means base MVA by rated MVA ultimately your per unit impedance of the utility. So when you go for utility impedance per unit impedance calculation, we need not to bother for the voltage. We have to see what is the base MVA and what is the system MVA. So from that we can calculate the utility per unit impedance. So utility per unit impedance in another way, simply you can say per unit impedance, that is equal to base MVA divided by rated MVA or short circuit MVA. So that equal to how much? 1 by 50. 1 is a base MVA and 50 is the rated MVA of that. So this is equal to 0.02 per unit impedance. That is we have put over here. Okay. That is a system per unit impedance at 415 volt level we put it. Now second point is your transformer. Transformer how much per unit impedance? Same way we have this per unit impedance on this 4.5% impedance means how much? Transformer per unit impedance based on the per unit impedance of the rated condition how much? This is equal to 4.5 means 4.5 divided by 100, that is per unit impedance based on this 500 kVA base. So we have last time we discussed how to per unit impedance from rated MVA to base MVA, how to calculate. That is your MVA, that is your per unit impedance, transformer per unit impedance based on the base MVA. If you calculate the base MVA, that is equal to how much? That is equal to your transformer per unit rated condition, that is equal to whatever the value, that into base MVA by rated MVA. That is the formula, that is the factor. Any percentage per unit impedance, any equipment per unit impedance, when you want to convert to a particular base, the formula that per unit impedance, whatever the rated condition, that is this is rated condition 500 kV. On that 500 kV base is impedance is 4.5%. So based on the base MVA, 1 MVA how much? That per unit impedance into base MVA by rated MVA. That's simple formula. So here how can we calculate? That means this transformer per unit impedance based on 1 MVA equal to transformer per unit impedance based on 1 MVA. On base per unit impedance, transformer base per unit impedance equal to how much? That is equal to transformer rated per unit impedance, that is a 0.045. That is a 4.5% is 0.045. That is into base MVA. Base MVA how much? 1 MVA. And rated MVA how much? Rated MVA is 500 kV means 0.5 MVA. So if you calculate this, it will come 0.09 per unit. That is the transformer per unit impedance based on 1 MVA. So that is we have put over here transformer, right? Now next part is a cable. Cable per unit impedance from the ohmic value, same formula like utility we calculated. So cable, suppose this cable is C1 per unit impedance, okay, at base, C1 base, that equal to how much? That equal to ohmic value how much? 0.001. That is ohmic value, that into your MVA by KVA square. MVA how much? 1. And what is the base KVA? KVA is a 0.415. That is square. If you calculate 0.001 into 0.045, it will come equal to 0.0059 per unit. That is the per unit impedance of this. If you calculate this, it will come 0.0059 per unit. That is we have put over here. That is the cable C1, right? Now come to the generator. Now on the second part, so these are the three equipment over here. On the utility part, utility, transformer and C1. We put these three here. Now the second part is the generator. Generator percentage is 10%. That is on the base of 500 kVA. So if we want to convert this percentage impedance to per unit value based on 1 MVA, so how much it will be? That generator base MVA, base per unit value, that equal to percentage impedance, how much? 10%. 10% on 500 kV base. Then this per unit, how much? 10% means 10 divided by 100, right? This is a per unit value, and this per unit value based on 500 kV. So this into base MVA. Base MVA means 1 MVA, right? And base kV and this rated MVA, rated MVA is a 0.5 MVA. So that equal to actually 0.1 into 0.5. That is equal to 1 by 5 equal to 0.2. So that is we have put over here. Generator per unit impedance 0.2. We got it. Then similarly the cable per unit impedance already we have calculated. This both the cable are identical. 0.00 ohm is ohmic value, and per unit impedance value we got 0.0059. We put the same 0.0059. Okay. Now this come to the second branch. Now here is a 0.002 ohm in this cable C3. So C3 and C4 same value. How we calculate this per unit value? C3 or C4 both have the same value per unit based on base MVA. We are calculated based on the base MVA 1 MVA. That equal to how much? Ohmic value 0.002. That into what is the formula? Base MVA 1 MVA by kVA square, that is 0.415. That is the ohmic value to per unit value conversion formula. That is equal to 0.002 divided by 0.415 square. So that is equal to 2 by 415 square. If you calculate this, it will come this value 0.0116. It is simply, it will come double of this. You see, it is a 0.001, it is 0.002, it is 2 times. So it will come, if you multiply by 2, you will get 0.0116. That is the cable value C3, C4, right? So we are getting this from value. Next, we have to calculate this. This motor and this motor are same. So this motor, how much this motor? This motor is a 25% impedance. So 25% means what is the impedance per unit value? Tali motor M1 based on the base MVA per unit equal to how much? 25% means 0.25 per unit, right? This into same formula, base MVA 1 and rated MVA 200. We already said that day 200 HP equal to 200 kVA. 1 HP, normally 1 HP equal to 1 kVA. Because most of the motor is power factor, we consider 0.8. So if you calculate 1 divided by 1 HP equal to, 1 HP is a 5. If you convert HP to kVA, HP the number of HP equal to number of kVA, because we consider power factor about 0.8. So this become 1 kVA. 1 HP become 1 kVA. So this 200 HP means 200 kVA means 0.2 MVA. So equal into 0.2 MVA. If you calculate this, it will come 1.25 per unit of the motor per unit impedance. Okay. So this is the motor per unit impedance that we put over here. So now the second branch here, that is equal to same as the 0.002 is 0.0116. It is also 0.0116 same. Then it is coming to the switch gear 2. This is a second switch gear. This is a first switch gear. Okay. Second switch gear. What is this cable? The same cable 0.002. That means 0.0116. Then there is a, from second switch gear there is a cable. Same cable 0.002 ohm means it is also same cable value 0.0016. This value we put it over here. Then we have the motor. Motor is a 1.25 per unit, 1.25 per unit impedance. We get it. Then we have a transformer here. Then we have a same cable, and then transformer. This transformer is how much? 250 kVA. So what will be the per unit impedance of this transformer? We can calculate it. So it is a second transformer TR2 per unit impedance based on the 1 MV. How much? Per unit impedance is 5% means 0.05, right? 5% is 0.05. This into Rated MVA 1 MVA by base MVA is a 0.25. If you calculate, right? So now from this we have to calculate the equivalent. How we'll calculate the equivalent? We have already said before how to calculate it. Now you see here. So when the fault is over here, who is feeding the fault? First is this utility will be, we are considering both are running in parallel. That is the maximum fault current. So now this is feeding this way. This utility is feeding fault current over here. Then this generator also feeding the fault current over here. So this is the one branch is feeding fault current. This is the second branch is feeding fault current. And we have already said this motor is also, when the motor is sudden, when there is a fault, immediately bus voltage will become 0. Here voltage become 0. So this motor will act as a generator and it will feeding the fault current. It will feeding the power. Instead of taking the power, it will feeding the power at this point. So that fault current will be supplied by this. So there will be another fault current over here. Similarly, this motor also feeding the fault current this way. Ultimately, it will go, this is a I4. That is a 4 branch of current. So total short circuit current on the fault point will be how much? I1 short circuit plus I2 plus I3 plus I4. This is the total short circuit current. This 4 branch of the current. So we have to calculate this 4 current from this equivalent circuit, right? So okay. So these are this. So this is a. So what we'll do? First, we'll calculate the total equivalent impedance. How much of the system total equivalent? Because these are the parallel. These 4s are parallel. So these 4 impedances are connected in parallel. So we'll calculate the parallel impedance. From that, we can calculate the total short circuit current. So how much parallel impedance will be here? There will be 4 paths. So if we consider this is a common bus, then one impedance is connected over here for the fault point. This is the one which is feeding current I1. So how much impedance? That is these 3 impedance in sum up, right? These 3 impedance sum up, how much it will be coming? You see here 0.02, 0.09, 0.059. If you calculate how much Z per unit equivalent for the utility, you can say utility total per unit. Okay, utility total per unit or Z per unit utility. You can write down Z per unit utility. That is equal to how much? That is equal to 0.02 plus 0.09 plus 0.0059. If you sum of these two, this will come equal to 0.09 to 11, right? 0.1159. That is a Z per unit coming for this path. Okay, so we can say these 3 together is coming how much? 0.1159. Okay, that is per unit impedance. Similarly, this generator how much coming? This is only 2, so it is a 0.2059, right? This 2 is coming 0.2059, right? Now this motor path how much is coming? This is coming sum of these two. Sum of these two how much? Sum of these two will be 0.0116 plus 1.25. That is equal to coming how much? It is coming, if you calculate this, 1.2616, right? 2616. That is a coming for this path. Okay. So this is coming your, this 3 is coming 1.2616, right? And then if you calculate this part we are not calculating, and then you have another, this 2 is this, then you have, this is a this path is a this one, this is a 2, this is this one, okay, 1 point, this 2 is a this one. Now the second motor M2, in case of second motor M2, this 2 is a 0.125. Along with this, for the second, there is another impedance over here, that is a plus 0.0116. This for 3 to be collected for the ZM2. This is for ZM2 per unit. Okay, ZM2 per unit. Additionally, another this one is added. So that equal to, if we add up all these 3, this is coming. How much it will be coming? Second motor will be coming approximately 1.27. You can say it is 1.26, 1.27 will be coming for the M2. It is a M1. M1 is coming 1.2616. For M2, these 3 together is coming 1.27. Okay, this is the impedance. Now this 4 impedance connected in parallel, right? So what we can do, we can delete this part, right? We can delete this part, that will be clear. So let's delete this part. So here, so this is our path. These are the four parallel path. This is one parallel path. This is one parallel path. This is one parallel path, and this is one parallel path. And this equivalent of this is the equivalent. Okay, that is a Z net per unit. So this is we can calculate equivalent of this. How much? 1 by Z net. That equals to 1 by Z1. If you say this is Z1, this is Z2. This is Z3, this is Z4. So we know the parallel formula, Z1 plus 1 by Z2 plus 1 by Z3 plus 1 by Z4. So that equals how much? 1 by 0.1159, right? 0 point 1 by Z2 equals how much? 0.2059. Then 1 by, you can say it is approximately both are same 0.7. It is coming how much? 1.26, right? 1.2616 plus 1 by 1.27, you can see. These are the four. If you sum this four, if you calculate this part 1.059, it will come equal to if the utility will be coming 8.33. Okay, this is coming 8.33. Then this will be coming 4.76 plus this will be coming, well, this is called 0.078. This is also coming approximately 0.078. So these are the coming total value. So if you sum of this, it will be coming 14 points. So it is 1 by, it is a total, not 1 by, it is a 4.76. It is a 4.7. It will coming about 14.65 if you calculate this thing. Okay, 14.65 will be coming this 1 by Z net. Okay. So now from this value, that means Z net is equal to 1 by Z net equal to 14.65. So this is the net value. So now we delete this thing. So we are getting 1 by Z net is equal to 14.65. Let it keep like this. Now the short circuit, now how we calculate the short circuit current? Now we can delete this part also. Now the short circuit current calculation is very simple. We know the base MVA. Base MVA equal to how much? Base MVA we consider 1 MVA, right? So fault MVA or short circuit MVA, that equal to base MVA divided by per unit impedance. Per unit impedance. So short circuit per unit impedance, we have got this. That is equal to short circuit MVA 1 MVA divided by per unit impedance Z net, right? That is the Z net. So this is equal to, we can write down 1 MVA into 1 by Z net. So 1 by Z net equal to how much? 4.14.6. That is 1 MVA into 14.65. So this is coming 14.65 MVA, right? That is coming our short circuit MVA. So if this is the short circuit MVA at what voltage level? At the rate of 0.415 volt, right? So from this, now we can delete this total part. Now from this, how much we can calculate? Now we know MVA short circuit formula ki MVA short circuit, this is equal to √3 into I short circuit into line voltage VL or V phase, V phase, because I into short circuit, that is giving the, it is a phase current, so it is giving line current. You can say phase voltage and line voltage are equal. Okay. So now this it is a 415 volt, is you can say √3 this. So now this is equal to how much? 14.65, right? That equal to √3 into I short circuit into voltage how much? 0.415, right? তাহলে I short circuit equal to কত হবে? I short circuit is equal to 14.65 divided by √3 into 0.415. If you calculate this, it will coming 14.65 into this will come approximately 20.37 or 38, you can say. That means this is equal to 20.4 kiloampere. Okay, the same like 20,400 ampere, which we got in the case of ohmic value. In the case of ohmic value, I short circuit we got 240 volt phase voltage and per phase impedance we got how much? We got per phase impedance actually 85.15, that is equal to your Z. So 1 by Z equal to how much? 1 by Z, that equal to 1 by Z equal to, it will be is 1 by 85.15, that is come 0.1174. If you calculate 0.01174, it is also coming 2400 ampere. So you can see in both case short circuit current is same whether you calculate by per unit impedance or per unit or ohmic method. Okay, so this is how to I have calculated for a simple network, but for any network if you want to do by hand method, you have to calculate in this way. Simple way is first you have to draw the circuit diagram. From the circuit diagram, for every equipment you have to calculate the per unit impedance. Okay, so per unit impedance for the utility, per unit impedance very simple. Per unit impedance equal to utility MVA, that is base MVA by utility MVA. Now for the transformer you have to calculate the per unit impedance. Transformer impedance always given by the vendor by the percentage. So percentage impedance you write down, from the percentage you can do the per unit divided by 100, that into MVA base MVA by rated MVA. For any equipment whose impedance given by percentage or per unit, for conversion to a per unit impedance based on the base MVA, that's per unit impedance the rated condition into base MVA by rated MVA. This is a simple formula for the, and it is mainly applicable for all the transformer, generators, motors, everything. For the utility only they give the voltage and fault level or voltage and short circuit current. This way the utility supply company they give the data in this way. But all other rotating equipment and transformer impedance always given in percentage value. So from that we can simply calculate percentage value divided by 100 into base MVA by rated MVA. Now for the cables it is giving in ohmic value. So for the cable from ohmic value to per unit value, how we calculate ohmic value into base MVA by base KVA square. So this is a per unit simple per unit impedance equal to per ohmic value into base MVA by rated KVA square or base KVA square. Okay, what about the base KV we are considering? Base KVA square, ohmic value into base MVA by base KVA square will be the per unit impedance of the cable. From that we can calculate all the component, all the equipment per unit value. Then you have to identify which bus you want to calculate the fault current. Identify that bus. Then you see who are the feeding the fault current. Identify all the feeding items, those who are feeding in parallel. So those circuit equivalent impedance you put in parallel path. Calculate the equivalent impedance. From the equivalent impedance, now we go back to our basic assumption. We consider base MVA 1. Whatever the base MVA we calculate, base MVA divided by this per unit impedance, net per unit impedance will give the fault MVA. From that fault MVA we use the formula √3 into short circuit current into voltage equal to fault MVA. From that you can calculate the short circuit current. So this is the way we do the calculation for the short circuit current. So this is for the symmetrical three-phase short circuit current calculation is completed both in ohmic method as well as per unit method. So this three video will help all of us to calculate the short circuit current of a particular network. I have given this just for your example, but based on the actual case, you can use this rule, and you can calculate the short circuit current for any network. So in a brief, up to this point under session 7, first video, we have elaborate all this impedance, how it can be represented, what is the relation, what is the meaning of impedance, what is the component of impedance, how the components are related. If you want to calculate the parallel impedance, instead of 1 by Z, we can use the conductance and subsistence, how the relation between conductance, subsistence and the impedance, that also we have demonstrated in the first video. Second video, we have calculated typical network whose short circuit current we calculated by ohmic method by converting all the impedance of various equipment cables in absolute ohm at that particular voltage. And today's session or today's video, we calculate the short circuit current using the per unit impedance. With this, our short circuit symmetrical fault current calculation is completed. Next video, under the same session, we will calculate the asymmetrical or unsymmetrical short circuit current, that is single phase to ground fault or two-phase to ground fault or three-phase to ground fault current, how to calculate, we'll do the calculation. In that case, we have to go for the unsymmetrical component, that is, we have to break this impedance into positive sequence, negative sequence, and zero sequence. From the zero sequence network, we have to calculate the zero sequence impedance. From that, we have to calculate the short circuit current, asymmetrical or unsymmetrical short circuit current, that we will discuss in the next video. Okay, thank you very much. Please look into this. If you have any doubt or question, please let me know, and keep on and share with your friends. If somebody is looking for this to know, it will be helpful for them. But I am reiterating that this is a simple, we do network, that's why we can do it calculation by hand. But when the network is very big, you cannot do this calculation by hand. In that case, you have to go by the computer software, and there are so many software is available in the commercial market, like ETAP. There are so many software nowadays available in the market, and there is a professional companies, those who have this software. Most of the consultant, they have this software, and they have a training from that software company, and they can calculate the short circuit current using that software. So, but basic conversion is remain same, idea is remain same, only for each software there is a tool how to do this calculation, how to operate it, that you need some basic training from that company. Okay, so this is all about the symmetrical short circuit calculation. Thank you very much indeed. Please keep it up and look into these videos. Thank you very much.